This is, again, one of 4 talks. Last day you saw linkage folding, and on Saturday you'll see Joe's talks about folding and unfolding polyhedra. This is a change in the schedule. This used to be Friday, now it's Saturday. So you'll have the double header folding hour on Saturday and a break on Friday just for the suspense building. Today we're going to do paper folding. So I think that all talks should either have animations or models, and this talk will have models. Last talk had animations, so brought some toys. We'll start out with some history definitions, and there's sort of 2 broad classes of origami results, computational origami results, that I want to talk about, or actually there are basically 2 kinds. One is sort of generally about foldability. I give you something, can it be folded? Or I give you some structure, can it be folded? And another is actually sort of designing something that looks like origami, sort of automatically by an algorithm. So paper and origami is old. The guess is that origami started, this is sort of a little history talk for fun. The guess is that origami started right about when paper was invented, because it's a natural thing. Before that, people were running on papyrus, and papyrus doesn't fold. I don't know if you've ever tried it, but hard to get papyrus these days. Paper was invented around 105 AD because 350 years before that, they invented the camel hairbrush for calligraphy, and they needed something to write on. So I'm serious. And then it spread from there. So it started somewhere in China. So there's a bit of a debate exactly where origami started, but one conjecture is China. Other conjectures are Japan and Korea. That's sort of where paper went from there. Eventually, it made its way over to Europe through the Spanish Moors, and by, where are we, 1690, there was the first paper mill in North America. And since then, it's become more and more popular. Traditionally, origami has been sort of, a school game or whatever, something to do for fun, but it's not really that serious. And particularly in Japan, it's hard to get good recognition for doing artistic origami. North America and Europe, and increasingly in Japan and other places, it's becoming more of an art form. And people are doing some really amazing stuff with origami. I'll show some examples. Part of what happened, I think, is in the last 25 years or so, people have started building a mathematical theory of origami. And using that, they've been able to build really complicated origami models out of like 1 square piece of paper with no cuts. And so I think these are intertwined, although it's not, it's hard to be explicit about exactly how the art ties to the math. But I think that's sort of the reason. To give you an idea of how limited things used to be, you used to have essentially 4 limbs per creature. So you could make something with a head and a tail and 2 wings. It's a standard flapping bird, and it flaps even. Or you could make something with a head and 3 legs, which is sort of like a dog or something. And it was pretty limiting. These days, you can do really complicated things. Here are some examples of some of the most complicated origami. There are like hundreds of miles of creases in this model. This is probably the most complicated model, the Black Forest cuckoo clock. But it's made of 1 piece of paper. It's made of 1. It's slightly rectangular. It's not a perfect square, I'm afraid, but no cuts. It's a big piece of paper. Incredibly detailed Black Forest. This was based on a real cuckoo clock that Robert Lang saw in the Black Forest. The pendulum, it's not a working clock, I'm afraid. It won't go back and forth. You have to provide the sound effects yourself. This is some very sort of curved paper folding, very expressive work by Erik Demaine. This doesn't even look like paper to me. It's just amazing. I was giving this talk to high school students once, and they said, "Whoa, dude, look at the pangolin." And this other kid said, "What's a pangolin?" That, of course. Some very expressive stuff, really amazing art in origami. I want to talk about the math side, which is somehow, how could you get a computer to make these amazing forms? So we need some, I should be a little formal about what it means to fold a piece of paper, or even what a piece of paper is, because it's a bit ideal compared to the real world. But for the most part, a piece of paper is this infinitesimally thin sheet. It's a two-dimensional surface that we play around with in 3D, usually. Usually it's in origami, especially in the West, it's usually a square, and you're not, in all of this, you're not allowed to cut. But we're computational geometers, so we like polygons. It might as well be a polyhedral surface. You can imagine taking a tetrahedron as your piece of paper. Why not? There's lots of interesting questions that come from that generalization. But a lot of the time, it's just a square. You crease it up. You fold it into some 3D shape or some flat shape. So this flapping bird, in addition to being three-dimensional, you can also collapse down. And I call this flat, even though it occupies a few layers. Let's see, what is a folding? Well, it should be isometric in the sense that you preserve the intrinsic geometry. If you look at any 2 points and measure their distance along the surface, it should be preserved. So you're not stretching the paper like rubber. And it shouldn't cross itself. And this is a little dicey to define precisely because you want to have this infinitesimal separation between layers. So like these two wings are very, 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 very close to each other. Okay? I don't want to be more precise than very, 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 very close. Yeah?
If you have 2 points each on every wing, then they're still considered the whole surface apart, like even if it's folded.
Yeah, I'm going to remember that these wings are separated from each other, even though geometrically they're sort of at the same place. Yeah. So there's some combinatorial information. And you can do that with infinitesimals or with some graphs or whatever. So that's the formal side, nothing too surprising. Now we can define configuration spaces like we did with linkages and say, well, I could just look at all of the possible foldings of my piece of paper. This is a big space. It has uncountably many dimensions. So it's a little hard to think about. And you're probably dreading the moment when I talk about locked pieces of paper that cannot be unfolded. Fortunately, the configuration space seems to always be connected. And so you don't really have to worry about the actual motions. So this is an example of a motion. It's very hard to construct an explicit motion of a piece of paper from one place to another. This was one paper that made that constructed such a motion. But you don't have to worry about it. At least for rectangular piece of papers, it's known that the configuration space is connected. And so provided you can show me a folded state like this and tell me, and I'll check that it's actually an isometry of the rectangle, I'll be sure that you can actually get here without you having to show me the motion. So, I mean, this is a folded state, and this continuous process is a folding motion. And I don't want to have to describe this motion in order to specify the flapping bird. I just want to have to specify the folded state. Okay, so this is a bit pedantic, but there's an open problem here, which is to do it for non-rectangular pieces of paper. For the most part, everyone just assumes this is true. And we can go on and talk about folded states because it's much easier. Good. Now, there's lots of terminology about foldings. In particular, the notion of creases is just where you have discontinuities in the derivative, so all of the edges in these foldings. And we usually draw the creases also on the unfolded piece of paper, so you can tell sort of where things go. And then for each crease, we can also distinguish whether it's a mountain crease or a valley crease. And you can label them here, conceivably, if I have the right button. Yeah. So, I mean, it's actually a little cluttered when you label them all. Usually we use dashed lines to show that they're valleys and dot dashed lines to show that they're mountains. It's not the greatest notation because they look almost the same, but it's the standard. All right, easy enough. And now we want to prove some theorems, after all, because this is mathematics. There are sort of three categories of theorems. The first I call a universality result, and it says, for some notion of what you'd like to fold, everything's possible. These are the coolest results. Not only that, there's an algorithm to tell you how to find such a folding, and everything you could possibly want is true. That's utopia. Then the next best thing is if not everything is foldable, at least you can tell when it's foldable by some polynomial time algorithm. But sometimes that's not possible, and you prove a hardness result that even to tell whether you can fold something is hard. Okay, this is something. The something that you're folding here could be anything, and in different contexts you get different kinds of results. But this is the high-level picture. Let's start out with foldability of crease patterns. So the idea here is I give you some crease pattern. This is a particularly simple one because it has only one vertex. And I want to know, can it be folded flat? So this is a basic problem in origami math. The input is, in general, the input is an embedded graph. But let's start with the simple case of a single vertex where the input is a sequence of angles. So I give you this angle, this angle, this angle, this angle. They sum to 360. Decide whether it can be folded flat. And probably this isn't obvious. I don't know if you've solved it already. Anyone have a solution?
Take plus, minus, plus, minus, plus, minus.
Oh, very good. Right. Take first angle minus the second angle plus the third angle minus the fourth angle, alternating sum. It should come out to 0, I assume you were going to say, because no, it should be 5, of course. So if you just sort of watch how you're moving along, if you're folding a circular piece of paper, a disk, in fact, you'll be moving along this arc. And if you just watch how much you travel, you go alternately plus theta 1, minus theta 2, plus theta 3, minus theta 4, and so on. You should end up back where you started, otherwise it doesn't close like a disk. So this sum should come out to 0. Another way to say that is that if you take the even indexed angles, they should sum to 180 degrees, because the whole thing should be 360. This is called Kawasaki's theorem. It's old. And that's the complete story if you're not told which creases are mountains and which creases are valleys. This is a necessary and sufficient condition. So that's kind of cool. But right, in this model, you're not allowed to have a crease flat. You have to fold every crease. Otherwise, the answer is always yes, you fold nothing. Right. Yeah.
This theorem only holds if you can fold the crease in either direction.
Right, so here, every crease is allowed to be folded mountain or valley. It's up to you for this to be sufficient. Now, if you're told which creases have to be mountains and which creases have to be valleys, there's more conditions. So let me tell them. One called Miyakawa's theorem says if you take the number of mountains at this vertex and the number of valleys, they should be, their difference should be 2 in absolute value. One way to see this is if you look at this polygon. Now it's a polygon on a circle, which is sort of on a sphere, but you can also think of it as a planar polygon. And just look at the total turn angle of this polygon. And you should know the total turn angle of a polygon is 360, except it might be clockwise oriented or counterclockwise oriented, so it's plus or minus 360. And if you look at the total turn angle, well, for every mountain, you turn, well, it's a little hard to see, I must say, from this figure. For every mountain, you turn plus 180. And for every valley, you turn minus 180. And so there's got to be 2 extra on one side or the other. Exactly.
Is that a necessary condition?
This is a necessary condition. It's not sufficient. So this is necessary for it to be flat foldable, but there's more. One other, in some sense, the entire rest of the story is that whenever you have a very small angle, like this one, surrounded by 2 very large angles, well, 2 larger angles. So this angle is surrounded by big bullies out here. And the necessary condition is that if the tiny angle is surrounded like that, those 2 creases surrounding the small angle have to have opposite signs. One has to be a mountain, one has to be a valley. It doesn't matter which way, but they can't both be mountains or both be valleys. This is the one-dimensional picture of what's going on. Here's a small angle drawn. So you can imagine this just being the perimeter of the paper. If this small thing is surrounded, when you fold it, there's crossing. Otherwise, you're OK. And you can apply this theorem repeatedly by saying, well, if I assign this as a mountain and this as a valley, or vice versa, and then I fold those two creases, I get a smaller diagram with fewer creases. If I keep applying this theorem, that characterizes all mountain-valley assignments that are valid flat foldings of a single vertex. So it's not obvious that that's true. I'll just tell it to you. And that's the full story for a single vertex. You can do this in linear time, I assume, definitely n log n. But single vertex is not very interesting. It's not usual that you get these circular pieces of paper, although there are some models with circular pieces of paper. But you'd like more. This just isn't that exciting. So let's do more complicated graphs. Yeah.
If there's only one vertex, then the shape of the paper shouldn't matter.
Yeah. It doesn't matter that it's a circle. Sorry. I was just making a joke. So there's a related notion to having one vertex foldable, which is locally flat foldable. Suppose I give you a big graph like this one. It's not a very big graph, but and now I cut out each of these vertices locally and see whether each vertex can be folded. That's local flat foldability. Certainly, if you're not told where the mountains and valleys are, it should be easy. You just check the Kawasaki's theorem. Well, that's not quite true, because what you need is a mountain-valley assignment for the entire graph that's consistent for each of the little vertices. That's the notion of flat foldability. I want one mountain-valley assignment, so this edge can only be either mountain or valley, and it's got to work on this side and on this side. And this is an example that does not work because of this odd cycle in the middle. This angle is smaller than the two surrounding angles, and so these two creases have to have opposite signs, and it's an odd cycle, and so you can't resolve it. In some sense, that's the only barrier, and there's a linear time algorithm to find whether there is a mountain-valley assignment that satisfies the whole thing. This is a result by Byrne and Hayes in '96. It's not so obvious. It uses some nice graph theory. I don't want to go into it because it's more tedious than enlightening. It's applying all of these rules that we just learned in a careful way to resolve if possible. But that's just local flat foldability, and it's pretty good in the sense that it tells you whether there is a geometry that things can be laid out and it would be folded flat. The hard part is that there may be non-local interactions. So you might fold something over here, and it collides with something over here. And that's not captured by local flat foldability, but you'd need it if you really wanted a flat folding. And there's no algorithm for that, or there's no really good algorithm for that, because the problem is NP-hard. This is another result of Byrne and Hayes. And I thought I would just give a little sketch of the hardness proof, because it's cool. It uses some nice little origami gadgets. So the idea is you take two parallel creases, and if you just have two parallel creases without specifying which is mountain and which is valley, you can either fold it this way or fold it this way. And I'm going to use that as a wire to communicate either a true signal or a false signal. And then this is some 3-sat reduction, where if you bring these wires together in this particularly strange arrangement. How many people have seen this diagram before? Good. Do you also know origami? No. Oh, interesting. So it comes up in other contexts, too. This is a classic thing in origami. It's called a triangular twist. So here it is folded. It's kind of a cute model. This is a particularly nice triangular twist I have folded here because this angle is 30 degrees. Here it's 35 degrees. 5 is any number bigger than 0. And the neat thing about this folding is if I fold it in this nice symmetric mountain-valley assignment, in the back, everything comes together at a point. And if you do it 35 degrees, they don't come together at a point. In fact, they collide with each other. It's not foldable. Okay, whereas other foldings like this one, where the triangle is underneath a little bit, do work, because in the back there's nothing going on. So that was maybe a little too fast. But the result is that these three things cannot all be oriented the same way. And this is a problem called not all equal 3-sat. They can't all be true and they can't all be false. You have to have 2 of one kind and 1 of the other, and then it folds. And then there's a whole bunch of other gadgetry to route these wires around, and that's also tricky, but that's the main idea. This is if you're not given a mountain valley assignment. The problem is also hard if you're given a mountain valley assignment that's known to be correct, and it's an even messier proof, so I won't describe it. So this is sort of bad news for testing foldability of crease patterns. And it says, well, in particular, it says if you're going to prove that some foldings exist, like this, you really have to describe the folded state, not just the crease pattern, because going from one to the other is hard. Any questions? All right. Let's go to another kind of foldability, which a little simpler, called map folding. There's this saying that the easiest way to refold a road map is differently. I'm sure you've all encountered this problem. You have a rectangular map in general. It's got horizontal and vertical creases aligned with the boundary of the paper, if you don't have a sadistic map manufacturer. And you want to fold it down to a packet of squares as it was originally packaged, hopefully. And the restriction here is you're not allowed to do any kind of origami fold. I'm only going to allow you to do simple folds, which is I pick a line like, so let me give another copy here. I pick a line like the red one, and I fold it over. Okay, that's all I'm allowed to do. In origami, you can do much more complicated things by simultaneous motion of several creases. Okay, but this is how we usually fold maps, so it's a natural restriction. This one can be folded as like this. In general, I might give you an arbitrary crease pattern, some graph in the plane. Is it flat foldable by simple folds? So we already know that in general it's hard, but these gadgets cannot be folded by simple folds. All of these creases have to be folded at the same time. So this is a natural, different problem. It's not easier or harder necessarily than that one. There's a couple of different kinds of simple folds. This is not so obvious unless you play with some more complicated models. This is in 1 dimension, so you can see what's going on. Here are the 3 layers of paper. I've taken a strip of paper and folded it back and forth on itself. And I want to look at a simple fold around this crease. And the simplest simple fold is to take just the first layer and rotate it around. And I get this picture. Is that clear? The second possibility is I take the top 2 creases and fold both of them around. And at the same time, because the bottom layer is connected to the 3rd layer, that comes with it. And that looks like this. Okay, this is the 3rd layer, this is the 2nd layer, this is the 1st layer. That's probably the hardest one to see. And the last one is you fold all 3 layers, and they just all move over there.
This is assuming that you have creases on all layers.
Yes, this is assuming you have creases in all layers. Otherwise, some of these won't be feasible. Yeah. So this is a 1-layer, 2-layer, 3-layer simple fold in 1 dimension. In 2D, it gets a little more complicated because one simple fold can be simultaneously 1 and 2 and 3 layer. But I don't want to show that. You can restrict that you're only allowed to fold 1 layer at a time, and that prevents these kinds of motions. Or you could restrict that you have to fold all the layers at once. That's what you normally do when you fold a map. You fold all the layers. Or you could say it's arbitrary, any one of these. And that's the sum layers model. And in each of these models, you get different results. This is the picture. So we've got all layers simple folds, some layers simple folds, and 1 layer simple folds. And over here, for comparison, we have general origami foldings. All I want is a folded state. I don't need a motion to get there. So we saw this Burn-and-Hayes result that it's NP-hard in 2 dimensions to tell whether there is a folded state. In contrast, in 1 dimension, you can do it in linear time because folded states are equivalent to 1 layer and some layer foldability. So this is not obvious, but it turns out to be true. this is work with several other people. Let's see, what else? Map folding. Oh, I should tell what the rows are also. So one-dimensional folding is pretty simple. You've just got a strip of paper. You can also think of that as folding a line. In 2 dimensions, we'll distinguish this case where you have a rectangle with horizontal and vertical creases and the more general case. And the positive results are that for these 2 models, basically you can do it in linear time plus maybe, or times maybe some log factors in all 3 models. But, and this is sort of the surprising part, if you take a map but then add diagonal creases at 45 degrees, it's NP-hard to tell whether you can fold it flat. Or if you take an orthogonal polygon with horizontal and vertical creases, it's also NP-hard to tell whether it can be folded flat by simple folds. So there's a big jump here between having orthogonal creases and general creases. Yeah, I didn't want to go into too much detail in these results because I'd like to get to origami design, but I do want to mention a bunch of open problems. There's a lot of open problems. Our hardness results that say in general in 2D it's NP hard are only weak NP hardness. How many people here do not know what weak versus strong NP hardness is? Oh, a lot. Yeah. OK, so weak versus strong NP hardness is about when you have problems where the inputs consist of numbers. And when the numbers are small, the problems are potentially fast to solve. When the numbers are very large, it's NP hard, but only when they're very, very large, like exponentially large in n. It's OK for numbers to be exponentially large in n because you're writing them in binary. So a pseudo-polynomial time algorithm is perfectly valid. Pseudo-polynomial is it's polynomial in the size of your numbers if they were represented in unary instead of binary. So weak NP hardness does not prove that pseudo-polynomial algorithms don't exist, if you want a double negative. I was thinking about this an hour ago, and I think the answer is no, that it's strongly NP hard, but it's just a guess. Let's see.
So Karmarkov's algorithm is then weakly polynomial?
Yeah, Karmarkov's algorithm is, I think it's called polynomial. It's not strongly polynomial. Yeah. So it's confusing. There's pseudo-polynomial, polynomial, and strongly polynomial. I didn't make it up. They're all slightly different. Yeah. OK. I said there was a quick jump from orthogonal creases, orthogonal paper, to non-orthogonal creases. But there's still a bit of a gap there. Probably the simplest form that we don't know how to solve is I have orthogonal creases and orthogonal paper, but they're not aligned. Orthogonal creases and rectangular paper, and just one's tilted 45 degrees. I have no idea how to solve that. OK, so that's simple foldability. If you look at more general foldability, just folded states, a nice open problem by Jack Edmonds, famous for his matching theory and other stuff in graph theory, is I give you a grid. I tell you which creases are mountains and valleys. I give you a map, and I tell you a mountain-valley assignment. Decide whether it can be folded flat. And that may be NP hard, and that would strengthen Byrne and Hayes' second result, that if I give you a mountain-valley pattern, deciding whether it can be folded flat is NP hard. But very interesting question. Seems very difficult even for a 2x(n) map, which is already easy to think about, but seems quite difficult to characterize. 1x(n) is solvable. We can talk more about it. It's one of my favorite problems in this area. You could also try to take our hardness results for simple foldability and try to make them work for general foldability. I haven't thought much about this, but it would be nice to make the Byrne and Hayes results simpler. I mean, these are fairly complicated crease patterns. Maybe you could do it entirely with orthogonal creases. That would be kind of cool. Questions? Solutions? Yeah. Yeah, here I had in mind that it's a square grid. Every cell is the same size. You can ask the more general question, and for a 1 by n grid, we can solve it when there's different sizes. But for starters, think about it with all the cells equal size. OK. Let's design some origami next. The most basic problem you might ask about origami design is I want to fold a horse or some polygonal silhouette. And this early paper by Byrne and Hayes, which sort of got computational origami started, was the first to pose this explicitly, but it's sort of all over origami. I want to fold this shape or that shape. How can I do it? Or is it possible? What polygons can be folded? A harder problem, as we encountered yesterday, is I want to fold a zebra or any two-color pattern. So I give you a polygon. I subdivide it into regions, half of which are, or some of which are colored black, other of which are colored white. I give you a piece of paper that's white on one side, black on the other. Can you fold it? Which two color patterns can be folded? And this has been looked at a lot in the origami world. These are a bunch of examples by John Montroll and some Japanese origamists. And I brought one of my foldings here. This is a 4x4 checkerboard. And it's folded from a square. White on one side and green on the other. And would anyone like to refold this? No one. Oh, so is it no one at all? OK, I'll have to pick a volunteer. All right. I'll need it back after. You have about half an hour. All right. I can't fold a zebra, but at least I can fold a 4x4 checkerboard. If you want to learn how to make that, ask me afterwards. Joe has some origami paper which he can bring in tomorrow. Hey, he's done it. Hold it up. Turn it around. Very good. All right. In general, what two color patterns can you make? Even harder is I give you a 3D object. Suppose I give you this polyhedron. I don't know what polyhedron that is, but it's one I found. Can you fold a square piece of paper into that shape exactly? Or which 3D polyhedron can you fold? I mean, this is a 3D polyhedron. This is a 3D polyhedron. Can you fold each of them out of a square piece of paper? But a polyhedron here, I mean something very general, just a bunch of polygons in 3D connected together.
Where can the boundary of the paper be?
Where could the boundary be? Well, the boundary can go on top of other things. It can be anywhere. I want the geometry of this thing, if I fuse together all adjacent layers, to be exactly that shape. But I can have multiple layers on the surface of the polyhedron. That's important. Later, Joe will be talking about the problem where I give you a polygon. I want to fold it into a polyhedron with exactly one layer for every side. Here, you can have many layers.
You're not allowed to have bits poking inside?
Here, you're not allowed to have bits poking inside. It's not just the visible stuff. You're in 4 space, and you can see on the inside of the polyhedron, just to make it harder. Other questions? So the problem is clear. How many, I don't know how to pose this as a question without giving away the answer. The answer is you can fold all of these things, always. So this is a universality result. I give you any polyhedron where each of the faces is colored either black or white, and it can be colored differently on both sides if you want. If you give me a really, really big piece of paper, square, if you like, I can fold it into exactly that shape with the right color showing at the right places. This is an old result with Martin Demaine and Joe Mitchell. You can also, there's a few algorithms for doing this, so this is also algorithmic. If you allow me to start with a rectangle, then I can optimize the paper usage arbitrarily well. So I can make the area of my original piece of paper be some additive epsilon away from the surface area of the polyhedron, which is the best you could hope for.
That's not bicolored?
Yeah, that's not bicolored. Thanks. Right, because, yeah, good point. There's some other things. For example, seams. Someone was asking about where the the boundary of the paper would go. If you look at this folding, there's some visible edges on the surface that are not part of this polygon. And so, you know, if you want a really nice model, those seams shouldn't be just anywhere. You'd like them arranged in some nice pattern, or maybe you could get rid of all of them. You can sort of put them wherever you want, is the short story. Basically, any convex decomposition of this shape. So here you wouldn't have any seams except along the edges, because all the polygons are convex. Here I want to give you a bit of an idea of how this is done, so that you don't think that this is actually practical, because it's far from it. The idea is you take a strip that's at the top there, a really, 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 really long rectangle. And if you start with a square, the first step is you fold it into a strip, okay, by accordion folding. So that's where it's not practical. If you have a strip, this is actually pretty practical. But if you have a square piece of paper, this is wasting, you know, all but a square root of n, 1/square root of n fraction of the paper. And plus, you've got a whole lot of layers, and once you start folding that, it's a pain.
So that's not compatible with the epsilon result.
Right, that's not compatible with the epsilon result. To get optimal paper usage, you have to start with a very, very long rectangle. And epsilon depends on the length of the rectangle. That's why I was cheating. But now, it's not cheating because I just revealed the secret. Fine. So this is some gadgetry, basically. There's 3 gadgets, which are fun to play with. By the way, you can get strips of paper. You can, like, adding machine printer tape. So at one point, I gave the talk with adding machine printer tape, and I demonstrated all of these models. I'll just point at them. If you want to turn your strip, it's coming in here, and you want to turn at some angle. It could be acute or obtuse. You can do it with 3 folds, a few folds. You can, if I have some convex region, this shaded region, and I have some paper that might go outside, if I keep folding along all of the edges of that convex polygon, eventually it will all be underneath. It's actually not obvious. It can take a lot of folds, but you keep going, and that will happen. And the last thing, which will reveal the color changes, is with a strip, it's actually pretty easy to flip it over. I mean, if you have a strip, you can just sort of twist it and squash it down. This makes a nice edge. And so the idea is you take your strip, you navigate around your polyhedron. Whenever you want to switch colors, you apply this gadget, turn it over, keep going. You just have to sort of paint the entire polyhedron. One way you can do that is taking a triangulation, we like triangulations, and just move your strip back and forth parallel to the next edge you want to visit. And just keep going. These are little turn gadgets, or very simple. When you get to the next corner, and let's say you want to go to this triangle next, you just apply a couple of turn gadgets, and you can start going to this one. You set up, I get to choose where I start going, this way or this way. I set it up so that I end up at the vertex I want down here. And the last layer may have some overlap because it may not be integral, but all of this works out. Question?
So the models you could make with this method wouldn't
Hold.
structurally stable.
These models would be far from structurally stable. That's right. I mean, they're not held together. You'd probably need glue for this to work. Except for flat. For flat, you could probably make it stay. But definitely 3D models, this would not hold together. But we're in 0G in this result. And then it holds together. Just don't touch it. All right. Anything else? Good. Even better, if you want to get the area result where the area, this excess paper that gets folded under goes to 0, you should pick a Hamiltonian triangulation. How many people here don't know how to take a Hamiltonian triangulation of a polyhedron? OK, a few. All right, enough that I'll, well, actually, I have no choice. I have to show the animations. So I can only hit forward. So suppose you triangulate your polyhedron. This is a pretty simple triangulation of a polyhedron. In general, it won't be a disk, but cut it up so that it is a disk. Then add a vertex to the center, just anywhere inside each of the triangles. Connect all of those vertices to the corners of the containing triangle, and also connect from each of these vertices to the midpoint of the adjacent edges. You now have a refined triangulation of your original triangulation, and it's Hamiltonian. Cool, huh? This is not an old result, but like 96 or so by Arkin and Mitchell and a few others. So now I'll visit the triangles in this order, and each one will get covered, and plus there'll be little epsilons of paper that I throw away, but this will get arbitrarily close to 0 paper wastage if the strip width goes to 0 and the strip length goes to infinity. Any questions? Okay, well, the natural question is, can you do better, something more efficient? In particular, with a square. So the title of the slide is, what if you start with a square? This is far from optimal. And indeed, there's no way, it's impossible to get the used paper goes to 0. That's easy to get. What you'd like is the wasted paper goes to 0. In particular, one nice problem is this checkerboard. Oh, hey, you folded it wrong. These are all green. Oh, there we go. This piece of paper is folded from, this checkerboard is folded from something that's only twice as large on each edge. It's pretty efficient. Conjecture is that it's optimal. Would someone like to refold this? Here you go. No, you've already had your turn. In general, for a k by k checkerboard, the conjecture is 2 over k by 2 over k, except when k is 2, obviously. And when k is odd, it's a little different. You have to put a +1 somewhere. There's a reason for this conjecture, which I won't go into, but it's very tricky to actually prove a lower bound. In fact, I'm not even sure that there's an upper bound known. Definitely for k equals 8, it's been done. But in general, I don't know. Any kind of wrapping problem, like if you have your tetrahedral gift, what's the best way to wrap it with a square piece of paper? As far as I know, no one's even, well, okay, definitely the optimal solution is known. I'm sure people have tried it. The only wrapping problem I know that's been solved to optimality is covering a cube with a unit square. Question?
I'm just confused. Do you really mean 2 over k or 2 over 2?
It depends.
No, it's a unit square, so.
Yeah, it's a 1 by 1 square, so it's going to get smaller as k gets bigger. The size of the checkerboard, yeah, whichever way you want to look at it. So lots of nice open problems here. These are nice order 1 problems, which you can think about. Cool. Well, let me tell you some positive news. This is sort of how pitiful it is, what we don't know. But we can do things pretty well, and in the context of something called an origami base. So this is something you would see at the beginning of any origami book. These are at least 6 of the standard origami bases. There's at most a couple more. For example, the flapping bird uses the bird base. And there's a model called the water bomb that uses the water bomb base. Probably a lot of you know it, and so on. There's nothing called the preliminary, I'm afraid. These are standard origami bases. They're very limiting. They basically only have 4 flaps for a certain technical notion of flaps. We'd like to make something more general. And the more general, this is an idea introduced by Lang, who's sort of the pioneer of computational origami, is to make a stick figure. So suppose I specify this tree. It looks sort of like a lizard in 1 dimension. And I also specify the lengths of the edges. So let's say I specify them all to be equal. And my goal is to find some base where all of the faces are vertical with respect to some xy plane. They're all above the xy plane. And when I plop it down to the xy plane, the projection into the xy plane is exactly the intersection with the xy plane. Okay, so it really touches the xy plane along this tree. Oh, it's also a tree. It's called the shadow tree. And that would be nice. This is called a uniaxial base. I have an example of exactly that lizard here. It's not a lizard yet, obviously. This is just a lizard base. And the artistic part of origami is to make this look like a lizard. And if you're Robert Lang, you can do this very easily. I can't. So this is a nice, it's a simpler version of the polyhedron folding problem. Polyhedron folding, I wanted anything. This is a particular 3D form. So I should be able to do this more efficiently. And you can. This is Robert Lang's work. And the key idea is something called the tree lemma, which is very simple. So suppose I take my square piece of paper on the left there and my desired base on the right, some hypothetical origami base. And I look at 2 points on the left that fold to vertices of the shadow tree. So they fold to somewhere in the bottom of this origami base. If I take a line connecting those 2 vertices on the piece of paper and I draw it with ink, and then I execute the folding, it'll make some path, polygonal path presumably, through the origami base. And I could project that path down to the xy plane and shorten it a little bit, and I would get something that goes directly between the 2 pink points. And if I project and shorten, of course, the path gets shorter. And so the result is the distance between these 2 pink points measured along this shadow tree on the bottom should be less than or equal to the distance on the piece of paper. And so this tells you, in some sense, when your piece of paper is too small. In particular, with this picture, that piece of paper ain't going to make that origami base because that's really short and that's really long. Right? So I should scale the paper up. So now I can start to formulate what I need. These are necessary conditions. So you can write them down. The unfolded distance between 2 points that correspond to these vertices of the shadow tree should be at least the tree distance. Tree distance provides a lower bound. The tree distance is given to us. We're given this tree, so we can compute the metric. And the surprising thing is that these conditions also seem to be sufficient. So for any placement of points on the unfolded piece of paper, so I can just say, well, I've got these vertices in the tree. I'll just put that vertex there and that vertex there and so on. And hopefully it'll work out. And the claim is all you have to do is check the tree conditions. This is unfortunately a conjecture. And this is where things get a little bit imprecise, to say it in a good way. The theorem is that if you do satisfy the tree conditions, then you can make a few changes and it will work. So that's almost as good. It's not yet known how to quantify what these slight modifications are, but at least you can prove that there are. And in practice, they're very slight. And so it's great for origami design. But there's definitely an open problem here to really prove this conjecture. And it's almost certainly true. So now let's sort of ignore this issue, because it can be dealt with somehow. And our goal is just to assign points on the right-hand side to points on the square so that we satisfy the tree conditions. And actually, that's not hard to do, because all we're really trying to do is get the scale right. We want to minimize the ratio of the size of the piece of paper to the size of the model. So let's scale one of them, let's scale the tree by a factor of lambda. That's a lambda, trust me. This is the font that people write comic strips with. And apparently, whenever they write a lowercase lambda in comic strips, that's what it looks like. Yeah. So if I allow myself to scale the tree down in size, then anything I choose will work. I can, for each of the vertices over in the shadow tree, I can assign corresponding points over there, and as long as they're not on top of each other, if I scale the tree sufficiently far down, this constraint will be satisfied. Okay, of course, some assignments are better than others, but now it's just an optimization problem. It's a hard optimization problem. It's some kind of nonlinear optimization, but any solution I find will work. And so I can just keep hacking away and trying to find some good heuristic solution. And this is what, so Robert Lang actually has a program that does this, I should tell you. It's freely available on the web. It's called Tree Maker. And it will do this optimization as best as it can and give you a crease pattern. And then you can fold something like this for any given tree. Right. Just to give you an idea of how hard this problem is, suppose I take this tree, the star where all the edges are the same length. then I've got to place points on the square so that all of these distances are at least 1, or actually at least 2. Because if I measure the distance between any two leaves, the distance is 2 over here, so it's got to be at least 2 here. This is one assignment that works. It should fit in this gray square. That is also known as, oh, I have this right here, disk packing in a slightly larger square. Equal radius disk packing. This is a known tricky problem. It's solved up to n equals 20 disks in a square, but I think beyond that it's open. So it's even harder than this problem. Oh, more?
27.
27. Oh, very good. Ron Graham has the latest.
There are more dots to the left than there are in here.
So one thing I forgot to mention, hopefully this will make my figure correct, is you only have to do this for the leaves of the tree. Am I then correct? Good. Yeah, so there's 8 leaves over here and 8 dots over here. Good. 9 would be much easier. Would have spent less time drawing this figure. OK. That's the scale optimization problem, just to give you an idea. You can apply it for this lizard. You get this assignment for the leaves for these points. And if you want, you can draw the corresponding disks. Actually, it's not exactly a disk packing here because it's not a star. Now we've got to somehow fill this in. And the first thing you can do is say, well, there's some edges, like from A to E here. This has distance exactly 2 in the piece of paper. And it has distance exactly 2 in the tree. So it's really tight. So that actually implies that this path from A to E, when you fold it up, will end up on the bottom of the folding. It'll be a direct path along the shadow tree. So that implies, in particular, B, this intermediate vertex better be right there. And you can keep doing that. And whenever you have these sort of taut paths where the inequality is met with equality, these are called active paths, you can place the dots corresponding to the internal vertices of the tree. And most of the time, these active paths decompose the polygon into convex pieces. Decompose a convex piece of paper into convex pieces. And the most of the time is this issue we got to before, where if that doesn't happen, you have to tweak the tree a little bit to make it work, to make these regions convex. Let's suppose they're convex, like they are in this example. Then we're going to solve each of these convex regions separately. Each one sort of represents a subtree of the whole tree. And the reason for all of this work of doing active paths and whatnot is that because you know this is along the bottom of the folding, you really know where these active paths are going. The interface between one of these foldings and another will work really nicely. Okay, I can be a little more precise after I tell you what we do in each of these. So let's take one of these convex polygons. I want to fold this one flat, or not flat. I want to fold this into a base whose projection looks like this, with all the right lengths. So what you do is you take your polygon and you shrink it while keeping all of the edges parallel to the original edges and keeping these distances equal. And you watch where the vertices go. And they'll move along angular bisectors as you shrink. And 2 things may happen. The first thing is that 2 vertices might meet, in which case your polygon gets smaller, and you just keep going. You also add these are called perpendicular creases because they're perpendicular to these pink edges from that vertex. You just keep shrinking up there, and eventually you'll finish. Another event that might happen is that another path becomes active. So it used to be that some of these paths were active, but that was it. Otherwise, we would have decomposed this polygon further. As you shrink, it may happen that there are now 2 vertices where the inequality is met with equality. If you shrink any more, you will no longer satisfy the tree condition, and then you know you're doomed to failure. So when this happens with equality, you better do something. And all you do is decompose your convex polygon into 2 convex polygons, and you recurse into the 2 pieces and keep going. You also add this crease for kicks, because it's necessary. And if you do all of this in this example, that's what you get as your crease pattern. So for example, if I take this quadrilateral region and I shrink it a little bit, at this point, at the dotted event, this path becomes active. We add in that crease and do each of the triangles separately. Any questions? This is a very quick description of TreeMaker, but hopefully it gives you an idea of how it works and what it does. Pretty neat ideas. The next topic turns out to be more related than you may expect. It's called folding in one straight cut. It's a very natural problem. It's the first problem I worked on in origami. Goes like this. I take a rectangular piece of paper. Shape isn't really that important. I fold it flat, however I like. I take my scissors, and I make one complete straight cut. What did you say? Almost a snowflake problem, right. This is like making snowflakes in grade school, except you only get one cut. Makes it a little harder. And so I get 6 pieces. One of them is an isosceles triangle, and another one, and another one. Somehow this never impresses people. And there's this other piece. It's just the complement. Let's do another example. So that was an interesting arrangement of triangles, but you can also make some pretty complicated shapes, like this swan. Thank you. I'll show you some more if you're good. In general, what shapes can you get and how can they be arranged? Natural problem. Has a very old history. There's this 1721 Japanese puzzle book that says, can you fold and cut that Japanese emblem shape out of a piece of paper? Answer is yes, there's a solution. Betsy Ross, I don't really have time to tell stories. You can ask me about the Betsy Ross story. She did 5-pointed star. So did Harry Houdini. He wrote this book, Paper Magic, or actually he probably somebody else ghost wrote it for him. But anyway, he may have performed this trick around 1922, where you fold, make one straight cut, get a 5-pointed star. Gerald Lowe is another magician. He wrote a book entirely about this problem, and he did the 5 arrangements of 5 triangles. He could do it 5 folds symmetrically, and all sorts of great examples. But it's all examples, and this is all recreational.
Is the cover a single straight cut?
I wish this was a single. Right, he did not do it. I've never tried. And then Martin Gardner wrote about this problem in 1960, and that's where we heard about the problem. He posed it as more generally, what shapes can you make? What are the limits of this process? And then we solved it. In general, you give me a planar graph. I want to fold it along some creases flat so that all of these edges lie on a common line. So then I just cut along the line and I'm done. So this is more general than just getting a shape. I really want that pattern of cuts. And again, you get a universality result. You can fold and cut anything. So if this projector screen were sufficiently flexible, I could fold it flat, make one straight cut, and get exactly this pattern of cuts and no more and no less, including this isolated point and this isolated segment and all sorts of great things. There are 2 methods for solving this problem. I'll just describe one here. The first one with Martin Demaine and Anna Libu is based on the straight skeleton, and it's actually very closely related to TreeMaker. So I'll show you that one. And another one with Marshall Byrne, David Epstein, and Barry Hayes is based on disk packing, okay, which is also related to TreeMaker, but in a different way. And I don't have time for that. Good. Straight skeleton is a very similar kind of idea that we saw with this stuff with Lang's work. Again, I'm going to shrink the polygon, but now my polygons aren't convex. So with convex polygons, everything's simple. But now we've got non-convex polygons, in particular, all of the regions in between the desired cuts. And for each one, I'm going to shrink it and see what happens. And basically, 2 things can happen. Either 2 vertices come together, like before, or in this example, at this point, this vertex touches this edge. And at that point, the polygon by itself splits into two subpolygons, and you recurse in the two pieces. So not too much harder. This is a notion developed by Osman Eichholzer and Franz Ohrenhammer for a different purpose, but then it works in this context. You also would like to define this object for non-polygonal regions. I mean, non-simple polygons, I should say. So in particular, there's the region that excludes this point, and I want to define the straight skeleton of that. Well, what I'll do is pretend that this point is a very tiny rectangle. As this perpendicular fold hits another edge of the straight skeleton, and what we'll do is reflect it. And it'll be perpendicular here. It'll meet another straight skeleton edge. We reflect. Of course, here's just going straight. We reflect again. We reflect again. Eventually, hopefully, it'll get out. These two lines are parallel, although that may not be obvious. And you keep going. Eventually, you fill in all of the perpendiculars. Takes a little while with your drawing program, but that's the crease pattern. And given an hour, you could fold this and cut out a turtle. Turtle's actually very hard. Here's some more examples. Let me show you another. So this came from a rectangle, you have to believe me. Just pre-folded it because it takes a few minutes. Ooh, it didn't work. There we go. Sorry, it ripped. That's an angelfish. I have the butterfly too, but you can see the butterfly, so that's no surprise. That's fold and cut. A little more is you can take 3 graphs for any value of 3 that are nested inside each other, fold this entire projector screen flat, and you get 3 parallel lines. If I cut along the yellow line, I get a turtle. If I cut along the pink line, I get a duck with an eye cut out. And if I cut along the cyan line, I get the star. And you can cut along multiple lines and get all of them. That's a bit harder. I think that's all I want to say about, no, surely not. Yeah, that's all I want to say about fold and cut. Any questions?
Have you done a sans serif alphabet?
Have I done a sans serif alphabet? No. Gerald Lowe actually did something like 18 of the letters, but not all of them. I've done a few, like this one. This was for a gathering for Gardner, number 5, Martin Gardner. So there's some sans serif letters. I mean, you could do anything. It takes a while to fold. It's a little hard to design one that's easy to fold, but you can do it. OK, and let me very quickly do flattening polyhedra because I have a model for it, and I want to use it because it's always a lot of fun. So flattening polyhedron. I take a surface of a polyhedron as a paper model. I want a flat folding. So this is a piece of paper. All I want to do is get it flat. How should I do it? A hammer. Very good. Squat. I heard step on it. So we got hammer, step on it, steamroller. Another suggestion. That's my favorite. This is in Thailand somewhere. I don't know why they were squashing Garfield. So you can do it. And what happens, hopefully that got on the microphone. Wouldn't want our listeners at home not to hear this great sound. It broke. And sorry, I mean, no cutting. That's cheating. I really want to fold this purely by folding. How many people here know the Bellows theorem, Bellows conjecture? OK, a lot. So forget the Bellows conjecture. I'm going to decrease the volume of this polyhedron purely by folding. OK, there's a subtle difference, which I don't want to get into. I want to get this folded flat, and I should have brought the model of how to actually do it without tearing. And none of these solutions work because they'll probably tear. OK, that's the informal argument. You've all done this with cereal boxes before. You probably know this folding. You step on it. It usually does this anyway. Come on, you can't tear your cereal box. Then you can't get the secret decoder ring.
But you have to break it. You have to pull open the bottom.
Right. Usually you break it. You don't actually have to. The trouble with cereal boxes, if you don't break it on one edge, it's airtight, and that makes it a little hard to do this. So you cut off a little corner, and then you can fold it this way.
Originally you opened it to get the cereal out.
Presumably you opened it to get the serial out. Very good. So hopefully it's not airtight. All right. You can see how often I play with cereal boxes. This is actually fold and cut in disguise. So in fold and cut, I wanted to fold, let's say, a polygon so that I lined up the edges of the polygon so I could cut along that line and get the polygon. But if you just look at the boundary of the polygon, you're folding it down to a line. You're folding it flat, if you will. The analogous thing in 3 dimensions is this is a tetrahedron folding. I take the surface of a tetrahedron. I want it to be folded flat now into 2 dimensions instead of 1 dimension. So this is really just the surface of a 3D fold and cut problem, which is great, except that we don't know how to solve 3D fold and cut. So a nice open problem there. So in addition, you would have to fold the interior of the tetrahedron through 4 space, flat, back into 3 space, so that you slice with your plane, and you get exactly the tetrahedron when you unfold. Tetrahedron, you could probably do it, although it's a little hard to imagine. In general, we don't know. We do know that all polyhedra homeomorphic to a sphere, so genus 0, can be flattened. And this is based on one of the 2-dimensional fold and cut solutions. So it turns out because a sphere is pretty 2-dimensional, you can use existing techniques. But as soon as you go to higher genus or some cell complex that doesn't have to be even a polyhedron, we don't know whether these objects can be flattened. But apparently, your caller does. Maybe you could ask him. Oh, she hung up. How rude. If you're going to get a call in the middle of a lecture, at least you could do is answer it. I'm kidding. Right. It would be even better to solve 3D fold and cut. There's a 3D notion of a straight skeleton. Maybe it solves it.
So but there's no folding motion, or is there? There's only a folded state. Or
Good question about the folded motion. OK, so we're now into question session, so I can go over time. This is all I have to say. So the Bellows conjecture says if you have a fixed set of creases and you just hinge along those creases, you cannot change the volume of a closed polyhedron. The difference is here, the creases can change over time. And that's enough to get a continuous motion. You don't believe me. All right, let me prove it to you. Where's the chalk? So suppose you have a tetrahedron. Volume can't change, right? Well, if you allow me to make various creases at various times, I can dent the top. And so I can define this function where I continuously push this down by some amount. Initially, it's pushed down 0. Eventually, it's pushed down a lot. I'm decreasing the volume as I do that. Every point is a crease point at some time. But there's only a finite number of creases at any one time. So that's why you can get a motion here, although we don't know that you can. That's this open problem. But at least it doesn't contradict existing theorems, which is good. Other questions about anything? Speechless. About anything. Yeah, it doesn't have to be. What was that? Will the Dow go up or down tomorrow? I'm not familiar with the Dow. What's that?
You can answer that for 2 cases.
I'll answer that tomorrow.
We'll do a little of each.
Yeah, it will go up and down, I'm pretty sure.
What's origami cube?
Oh, what's origami cubed? Have you seen the back of this T-shirt yet? It's much cooler. Origami cubed is the 3rd Origami Science, Math, and Education Conference. It was 2 years ago. This conference is held roughly every 5 years. So I've only been to one of them. But it's sort of one of the... You should get the proceedings of this if you're interested in origami math. It's by A.K. Peters and has lots of the latest stuff. Other questions? Great. Time for dinner. So this is by, oh boy, this is called the Mars folding or something. I don't know why. By this guy in Japan. Oh, why can't I remember the name? And
Pretty nice.
it's a very, very nice map folding. I mean, so it opens up to the whole thing automatically by itself. You just have to pull. It's like a pop-up card. But yeah, it's hard to get these. Oh, in New York City even.
Well,
Good.
they have
They're more popular in Europe. Probably a lot of the Europeans here have seen them before.
Good. So I'd like
All
to
right.
thank our speaker one more time. And